Hello and welcome. Today, we are going to dive into a fundamental concept in electrical engineering and physics, the phasor. If you've ever looked at alternating current, or AC circuits, you might have found the math a bit tricky, with all the sine and cosine waves. Phasors are a powerful mathematical tool that simplifies all of that. By the end of this, you'll understand what a phasor is, how it's represented, and why it's so incredibly useful. Let's start with the main idea shown in our notes, the mathematical representation of a phasor. A phasor can be represented in two primary ways: first, the rectangular form, and second, the polar form. But before we get into those forms, what exactly is a phasor? As our notes state, a phasor is a complex number that represents the amplitude and phase of a sinusoid. Let's break that definition down. A sinusoid is just a fancy name for a wave that has the shape of a sine or cosine function. Think of the electricity coming from your wall outlet. It's an alternating current that follows a sinusoidal pattern. These waves have two key properties we care about for this discussion. First, the amplitude, which is the peak or maximum value of the wave. In our notes, this is represented by the term V sub m. The m stands for maximum. Second, the phase, which is represented by the Greek letter phi. The phase tells us the starting position of the wave at time 0. Is it at its peak? Is it at 0? The phase angle tells us exactly that. The full time domain expression for a sinusoidal voltage is written as V of t equals V sub m times the cosine of omega t plus phi. Here, omega is the angular frequency, telling us how fast the wave oscillates. Now, working with these full cosine functions can be very complicated, especially when you need to add or subtract different waves. This is where the phasor comes in to save the day. A phasor freezes the wave at a moment in time, specifically, at t equals 0, and captures only the two essential pieces of information: its amplitude, V sub m, and its phase, phi. It cleverly removes the omega t part from our calculations, because in most circuits, the frequency is constant for all components. So, let's explore the two ways we can write down this phasor. First, we have the rectangular form. The notes show this as z equals x plus jy. Here, z is the standard letter used to represent a complex number. A complex number has two parts. The first part, x, is called the real part. You can think of this as the horizontal component of our phasor. The second part, y, is called the imaginary part. It's multiplied by the letter j. J is the imaginary unit, which is defined as the square root of -1. In mathematics, you might see this written as I, but in electrical engineering, we use j to avoid any confusion with the symbol for current, which is also I. So, the rectangular form, x plus jy, is like giving coordinates on a map. You go x units horizontally along the real axis, and y units vertically along the imaginary axis. Why is this form useful? As the notes point out, the rectangular form is excellent when you need to perform addition or subtraction of phasors. You simply add the real parts together and add the imaginary parts together. It's very straightforward. Now for the second way to represent a phasor, the polar form. The notes show this as z equals or at an angle of phi. Let's break this down. Z is still our complex number. R represents the magnitude of the complex number. This is the straight line distance from the origin, or 0, directly to our point. For a phasor representing a voltage wave, this magnitude R is simply the amplitude of the wave, which we called V sub m earlier. The Greek letter phi represents the phase of the complex number. This is the angle that the line makes with the positive horizontal axis, or the real axis. So, while the rectangular form gives us coordinates, the polar form gives us a distance and a direction. Go out our units from the center, at an angle of phi. Why is this form useful? The polar form is fantastic for multiplication and division. To multiply two phasors, you multiply their magnitudes and add their angles. To divide, you divide their magnitudes and subtract their angles. This is much simpler than trying to multiply or divide them in rectangular form. Our notes also show a third, related form called the exponential form. This is written as z equals or times e raised to the power of j phi. This is mathematically equivalent to the polar form and is based on a famous relationship called Euler's formula. It's another compact way to write the magnitude r in phase phi. Now, let's look at the diagram showing the representation of a complex number. We have a horizontal real axis and a vertical imaginary axis. A phasor z is drawn as an arrow, or a vector, starting from the origin. The horizontal projection of this arrow is x, the real part. The vertical projection is y, the imaginary part. The length of the arrow itself is r, the magnitude. And the angle it makes with the positive real axis is phi, the phase. This diagram perfectly illustrates how the rectangular form, x and y, and the polar form, r and phi, are just two different ways of describing the exact same point. This brings us to a very practical question: how do we convert between these two forms? Let's say we have the rectangular form, x plus jy, and we want to find the polar form, r at an angle of phi. To find the magnitude r, we use the Pythagorean theorem. As you can see in the diagram, x, y, and r form a right-angled triangle. So, r is equal to the square root of x squared plus y squared. To find the angle phi, we use basic trigonometry. The tangent of phi is the opposite side, y, divided by the adjacent side, x. Therefore, to find the angle itself, phi is equal to the inverse tangent of y divided by x. So, with these two simple formulas, you can easily convert from rectangular to polar form. Now, what about going the other way? Let's say we have the polar form, r at an angle of phi, and we want the rectangular form, x plus jy. Again, we use basic trigonometry from the same right-angled triangle. The real part, x, is the adjacent side of the triangle. So, x is equal to or times the cosine of phi. The imaginary part, y, is the opposite side. So, y is equal to or times the sine of phi. With these two formulas, you can convert from polar back to rectangular form. This means we can write our complex number z in several equivalent ways: z equals x plus jy, which is the same as z equals r at an angle of phi, which is also the same as z equals r times the cosine of phi plus j times the sine of phi. They all represent the same phasor. Finally, let's look at the last diagram, which shows a practical application, a phasor diagram representing voltage and current in an AC circuit. We see the real and imaginary axes. There are two phasors shown. The first phasor is for voltage, labeled V. It has a magnitude of V sub m and a positive angle phi. The second phasor is for current, labeled I. It has a magnitude of I sub m and a negative angle, written as negative theta. The diagram also shows an arrow labeled with the Greek letter omega, indicating a counterclockwise direction of rotation. This reminds us that these phasors are a snapshot of waves that are constantly rotating at a frequency omega. However, for our analysis, we just look at their frozen positions. Because the voltage phasor V is at a positive angle and the current phasor I is at a negative angle, we can describe their relationship. We say that the voltage V is leading the current I. Or, equivalently, we can say that the current I is lagging the voltage V. The difference in their angles tells us exactly how much one leads or lags the other. This relationship is critical for understanding components like capacitors and inductors in AC circuits. To summarize the entire concept, look at the final conversion shown in the notes. The time-consuming, complex expression from the time domain, which is v of t equals v sub m times the cosine of omega t plus phi, is beautifully simplified into the phasor domain as v equals v sub m at an angle of phi. We've transformed a difficult calculus problem involving oscillating functions into a simple algebra problem involving complex numbers. We can now easily add, subtract, multiply, and divide voltages and currents using the simple rules of rectangular and polar forms. Once we've done all our calculations in the simple phasor domain, we can convert the final answer back to the time domain if we need to. This is the power and elegance of the phasor. It's a tool for translation, taking a complex problem, moving it into a simpler world to solve it, and then translating the solution back. Thank you for joining me in this detailed exploration of phasors. I hope this has made the concept clear and shown you just how useful this mathematical tool can be.